In this video, we're going to talk about factoring special binomials. All right, factoring special binomials. And I want you to remember that binomials are polynomials with two terms. Before we get too involved into actually factoring special binomials, I want to review what we call perfect squares. These are the numbers that come from squaring another whole number. For instance, if I square the whole number 1, I get 1, right? Because 1 times 1 is 1. If I square the whole number 2 squared, I get 4. That means 4 is a perfect square. If I square the whole number 3, I get 9. That means 9 is a perfect square. So far we have 1, 4, 9, and I can continue to go through until I can not write anymore. I've gone through 15 squared to list a bunch of perfect squares: 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. Those are all perfect squares, and all of these numbers are numbers that I want you to get acquainted with so that you can kind of recognize them in problems where we'll have binomials, all right? Because this is going to lead us to the first method of factoring special binomials, which we call a difference of squares. We've actually already learned how to factor this, and it basically comes from when we multiply. Back when we started talking about multiplying polynomials, and I'd say that there's a couple of special products you get when you multiply two binomials, and it came in the form of a plus b times a minus b. Now, just to recall what that formula is, I'm going to come over here and I'm going to multiply a plus b times a minus b. And remember, we call these conjugates, all right? But when I multiply, you can use the FOIL method or, repeated distributive property. A times a is a squared. A times negative b is negative ab. B times a is ab. Notice that I can write it as ab or ba. Right, because that's the multiplication in order, doesn't matter. And then b times negative b is a negative b squared. Of course, we have to combine these two middle terms since they're like terms. Well, they're basically the same thing, as one's positive and one is negative. That means they cancel out, and that means that our result is going to be a squared minus b squared. All right? And so this is going to be a squared minus b squared. This is how we're going to factor. Anytime we have a problem where I have some quantity or some expression squared subtracted from another expression squared, then I'm always going to take whatever is in the first spot that I'm squaring and put it in these first set of parentheses here in order for me to factor. And then I'm going to take the second thing that I'm squaring and I'm going to put it in the second set of in the second spot in my set of parentheses so that I can factor. Let's look at a couple of examples. In these two examples, we're going to factor. That's my only instructions. In my first example, I have x squared minus 36. And so what I need to do is I need to figure out if I have a difference of squares. I can definitely see that I have a difference, right? Difference means subtraction. And I can also see this x squared here. Now I got to figure out what I'm squaring in order for me to get this 36 here. Remember, I told you to memorize these numbers here. Notice that 36 comes from 6 squared. And so what I can really do here is I can write this as x squared minus 6 squared. And now I can see that this is almost perfect for my formula, right? Instead of a here, I have an x. Instead of a b here, I have a 6. So if I'm going to factor that, it's going to factor into an x in these first spots and a 6 in these second spots. One's going to have a plus, one's going to have a minus. X plus 6 times x minus 6. All right, and that's how I factor that binomial there. Let's go to the second example. I have 36a squared minus 169b squared. Again, I want to see if I can write this as a difference of squares. And one clue that I do have a difference of squares is that I have a variable squared here and a variable squared here. And not only that, but let's look at these examples here, right? In this example here, a cubed minus 216, right? I want to write this or make sure that this is a difference of cubes. Notice here I do have a variable cube, so that's a good sign that I'm going to have a difference of cube, and I also have that subtraction there. I want to make sure that this is a perfect cubed here. 216 is actually 6 to the third power, and so I can really write this as a cubed minus 6 cubed. All right, and so I'm going to remind myself of that formula: a cubed minus b cubed equals a minus b plus a squared times a squared plus ab plus b squared. All right, notice here the a is in the same spot as this a here, so I'm going to put it right here, and right here. This 6 here is in the spot for this b, so I'm going to put it right here, and right here in that formula. And so what I'm going to get here is an a minus 6 times an a squared plus a times 6 plus 6 squared. All right, and I can simplify that a little bit more. It's going to be an a squared plus 6a plus 36. And that is considered to be factored completely. Let's look at another example. I have 8x to the third power minus 125y to the third power, right? Notice here, 8 is a perfect cube. It comes from cubing 2. X is a perfect cube. It comes from cubing x. 125 is a perfect cube. It comes from cubing 25. And y is a perfect cube. It comes from cubing y, right? And so what I'm going to do is I'm going to rewrite this as 2x cubed minus 5y cubed. And again, the only reason why I'm writing it this way is so that I can see the actual a cubed minus b cubed. Right? That way I can see what's in my first spot that I'm cubing and what's in my second spot that I'm cubing, so I can explicitly put it into the formula a minus b times a squared minus plus ab plus b squared, right? I'm going to put the 2x in the place of the a here, and I'm going to put the 5y in the place of the b here. And I'm just going to simplify after I'm done doing that. So let's look at it. I'm going to get a 2x minus 5y times, I have to square my a, which is 2x. So I'm going to do a 2x squared. Notice I put it in parentheses there because I have to square the 2 and the x. All right. Plus, I'm going to have a 2x times my b, which is a 5y, minus a 5y quantity squared, and I can close my parentheses there. All right, and the rest is just simplifying, right? I get a 2x minus 5y times a 4x squared plus 10xy plus, I'm sorry, there's an error here. That should be a plus sign. Notice here that I have pluses in both sets of these parentheses here. So that should be a plus, and that should be a plus. And that should be a 25y squared. And that is completely simplified. All right, it's factored and factored completely. The last way to factor when I have special binomials is to do a sum of cubes. All right, and the formula for a sum of cubes is very similar to the formula for a difference of cubes. The only difference here is that it's going to start out with an a plus b. And it's going to have an a squared minus ab plus b squared. All right. So the differences in signs are here. Instead of a minus like we did with the difference of squares, we have a plus. And here, instead of a plus like we did with the difference of squares, we have a subtraction. All right. And so we'll look at these last two examples. It's going to work the exact same way. The only difference is our signs here and here are going to be different. All right, I have m to the third power plus 343. Notice m is a perfect cube, and 343 comes from cubing 7. And so one way to write this is to write it as m cubed plus 7 cubed. All right, and when I write it that way, my m goes in the place of a, and my 7 goes in the place of b, in all of these places in this formula here. And so if I do that, I'm going to have an m plus 7 times an m squared minus an m times 7 plus a 7 squared. If I were to simplify that, I get m plus 7 times m squared minus 7m plus 49. And I've completely factored that special binomial. Our last example we're going to look at in this video involves 27x cubed plus 512y cubed. Notice here 27 comes from cubing 3. We know x cubed is perfect. And 512 comes from cubing 8. And we know y cubed is perfect. And so one way to rewrite this, okay, is to write it as 3x all cubed plus 8y all cubed. Notice that they are all cubed, meaning we have our a cubed plus b cubed from our formula up here, right? And so I'm going to put the 3x in the place of a in these 3 locations, and I'm going to put the 8y in the place of b in those 3 locations. And when I do that, I'm going to get something that looks like the following. I'm going to get a 3x plus 8y times a 3x quantity squared, right, plus a 3x times 8y plus an 8y quantity squared, and I'll close off that parentheses. And so this is going to equal 3x plus 8y times, when I square the 3 and the x, I get a 9x squared. 3 times 8 is 24. X times y is xy. And 8 squared is 64. And of course, I have that y squared there. And that is how I factor that binomial there. All right. Notice that we did not have a sum of squares. Okay. And notice we will never have a sum of squares. They can't be factored. Any sum of squares, something like x squared plus 49. Notice that that's x squared, which is perfect, and 7 squared. There is no way to factor that without using what we call complex numbers. And since we're not using complex numbers, we will never factor these, all right? And so whenever I encounter a sum of squares, I automatically know that that polynomial is going to be prime, meaning it can't be factored, all right? Notice also that I didn't do any powers that are higher than 3 and 2. All right, any power that's higher than 3 and 2, if there's a sum and a difference, let's say a difference of fourths or a difference of 6 or a sum of 6, then I can make them be a sum of a difference of squares, a difference of cubes, or a sum of cubes, if both are perfect 6 and perfect fourths. Otherwise, I can't factor them as well. And we'll look at examples that are similar to those as we get to the next section in our chapter. But this concludes our videos on factoring special binomials.